Hi and welcome to this short video where I'm going to demonstrate how to find the derivative of this function y equals e to the x. Before we get into that, I just want you to look at this curve. You might remember in the past that if we wanted to find a rate of change at a particular point, we tended to just draw a gradient at that line, a tangent firstly, and then find the gradient of that tangent. You can see what I've done here, and you can see that the tangent here provides a positive gradient, which is relatively small. If we move to a point on the right of my y equals e to the x curve, again, draw a tangent to that line, and you can see again that the tangent is a positive one, but this time it seems to be increasing. It's of greater magnitude than this one. And again, if we go to a point here, once again draw a tangent, you can see that I've still got a positive rate of change, and it's larger than either of these two. So we're getting progressively larger rates of change as we move to the right on this function y equals e to the x. Okay, so if I was to find what that rate of change was, a general expression, what would it look like? Well, we're going to look at two pieces of information, both of which you've seen before. And the first one deals with this: the limit as h approaches 0 of e to the h minus 1 all over h. Now, we've been told in previous videos, and I've shown it in the previous video, that in fact if we were to substitute 0 into here, that would approach 1. Obviously we can't do a direct substitution because what you find is e to the e to the 0 will give you 1. We subtract 1 from it and our numerator is 0. We then divide by 0 and that gives us problems. So we have to do something slightly tricky, and that's where we just substitute for h equals a very, very small number, which is in fact very close to 1. I'm going to make it this one. So if I substitute into there, let's just go to our calculator, and I go e to the power of that very small number minus 1, evaluate that, so there's that small number, and I divide it by that value of h, which again that's the very small number. You see that it does approach in fact 1. Okay, and the closer and closer we get to 0, the closer this limit will be to 1. So we can see that this thing itself is in fact going to equal 1. So that's the first bit of information. Now the second you will have seen before, and that is derivatives by first principles. Now hopefully this will be one of the last times you actually see this, but you might recall that if we take the limit as h approaches 0 of our function, we can find the derivative of it. Now remember, our function here is e to the x, so f of x plus h will be equal to e to the x plus h. So I'm going to substitute in here. So there's my limit as h approaches 0 of f of x plus h, so that's e to the x plus h. And I'm going to subtract f of x, and that's all over h. I'm now going to break this apart, so that's e to the x by e to the h. You might recall that if we've got two bases multiplying by each other, you add the indices, and that's what I've done, or undone at this point. Looking at these terms, I can see e to the x is common, so I'm going to take that out the front. And then I'm going to take this out the front again, so that e to the x will come out the front. Okay, so you recognise that this portion here is exactly what we found up here, and we've said it's going to equal 1. So that means we've got e to the x times by 1, or just e to the x. So the derivative of y equals e to the x is in fact e to the x. And we saw this to a degree up here, that as we moved our function across to the right, the rate of change actually increased and it got larger and larger. In fact, it got larger and larger exponentially, and that's what we've just determined. So in summary, if we know that y equals e to the x, then we can show that dy dx also equals e to the x. Thanks very much for listening.